Okay, welcome back, Science 10s, to our next unit, which is going to be looking at physics. Previous units that we've covered was biology, which is looking at the study of life in the universe. We also looked at chemistry, which is looking at what the universe is made of. And you might recognize this diagram in the background, looking at protons, electrons, and what everything is made of. But what we're going to be looking at in physics is the rules by basically how all these things work. So this could be from big things like how cars move and people move, or even how planets move, all the way down to also how atoms move and how electrons and neutrons move and things like that. And the two big concepts we're going to look at in physics are motion and energy. And our first chapter is going to be looking at motion, and our second chapter is going to be looking at energy. But today we're going to start with our first chapter. It's the fifth chapter in this course. So 5.1 today, we're going to look at motion, and today we're going to start with looking at position. So position just means where you are. So we have a person here, they're standing, looks like maybe a park in a city. That is their position, where they are right then. But when looking at position, it might be important to consider what position we were at before, what position we will be at later, and how our position has changed. So maybe if you're talking to someone, this person said that in the morning, their position was changing. They went for a 3.5 kilometer run in the morning. That person said, wow, like good for you, that's a really good job. What I want to know about this one is they said where their position was before and how it's changed, but they didn't give any details about what direction it went, because in this case, it doesn't really matter. They just say that they went 3.5 kilometers. That could mean that this person ran all the way to the city and came back. It could mean that they went this direction and then came back. It could mean that they just went back and forth, back and forth, back and forth, back and forth there until they ran a total distance of 3.5 kilometers. This person doesn't really care because they know the difficulty of running 3.5 kilometers in any direction is about equal. So this is an example of when we're changing our position and we're not interested in the direction. Values like this, where we don't really care about the direction, are called scalar quantities. They're looking at the magnitude only. The magnitude just means the amount or the value. So 3.5 is the magnitude there, 3.5 kilometers. Direction is not applicable or it's not considered. So we're not worried in that last example about direction. Other places where it's not even applicable would be things like mass. You don't have like 10 kilograms up or down or left or right or north. You don't have degrees Celsius, like temperature, that would be like 20 degrees to the left. Well, you would have measuring an angle, but 20 degrees Celsius wouldn't have a direction to it. Distance is also this example. So when I talked about how far someone went, and that's their distance, we're not interested in what direction it was, just how far they went. So that's what scalars are, but there's another quantity called vectors, and this is when we do worry about direction. This was kind of made a little bit more public or known when the villain in Despicable Me's name was Vector, and he actually describes what a vector is pretty perfectly.
I'm applying for a new villain loan. Go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
So that's what a vector is. He described it pretty much perfectly. It considers direction and magnitude. So before we had magnitude from scalar, that's the number, but then we also have to consider direction. So examples like this are like acceleration. For example, the acceleration of gravity is about 9.81 meters per second squared downwards. It would be very different if this was 9.81 meters per second upwards, if you dropped a ball and it shot up at 9.81 meters per second squared. So direction is important for acceleration. Force is also important. The direction that you push something will definitely have an effect on what direction that it moves. And then displacement. This sounds a lot like distance, but it's pretty much the same except for we are considering the direction that we ended up. So let's look at an example to see what displacement looks like. So say that someone's initial position was starting right here at Leduc Composite High School in Leduc. And now we're not just worried about how far you go, but you're trying to end up in a certain position. So say you're trying to get to the public library over here. How you would tell someone how to get there is that they would have to travel pretty much directly north to get to that position. And let's say they say that's about 2 kilometers. So the distance you have to go is 2 kilometers. But if the only information you gave was 2 kilometers and did not worry about direction, someone might travel off in this direction, going kind of northeast, and they end up over here, which is a significantly different position than the library where they wanted to end up. So even though they correctly went 2 kilometers, their distance was the same, they ended up in a different place, so their displacement is different because they're in a different direction. Now you could also have an example where you have a different distance but the same displacement. So let's say that this person takes this route to get to the library. If we add up all these distances here that they traveled, they went a much larger distance than just going straight to the library. However, they started here and ended up here. They ended up in the same position that they wanted to. So their displacement is the same as if they just went straight there. Where they started to where they finished is going to be the same. So they have the same displacement, but they had different distances to get there. So that's what this lesson is mostly focusing on, the difference between distance and displacement. So distance is the total length of the route traveled, or it's like for how far you went. The symbol that we're going to use for this is just d. Displacement is the change in position from the start to the end. So where you ended up compared to where you started. Now the symbol looks a little bit different. So it still has the D, but this actually represents position in this case, and the triangle represents change. So it's going to be a change in D, which is representing position here. So how your position changed from where you started to where you ended. Now there's also that arrow on top. All that that arrow means is that this is a vector quantity and that direction is important. So that just means it's a vector. All right, I'm going to use those symbols for this lesson because otherwise D would just look the same as D if I didn't include those symbols. So I'm going to use those there to differentiate distance and displacement. So let's look at some examples. Determine the distance and the displacement in the following examples. The first one is a car drives 20 kilometers north. Okay, so it's always good to just draw this out to see what it looks like. This one's pretty simple. Say this circles the car. They drive north 20 kilometers. Okay, everyone's supposed to find the distance. I'm just gonna put D is equal to how far the total length of the route that they traveled, which is 20 kilometers. Not too hard. Then I look at the displacement. Put those symbols of a triangle and an arrow. Say this is our displacement. They went 20 kilometers. North is where they end up compared to where they started. These look almost identical except for that I included direction. And when traveling in a straight line, that's the only difference. Let's look at another example though, where we went 10 kilometers east and then 20 kilometers west. So I'm gonna draw this out. We start right here. We go 10 kilometers east, 10 kilometers, and then 20 kilometers west. Okay, now if I look at the distance, person went 10 and then an additional 20. So they drove a distance of 30 kilometers. Okay. When I look at the displacement, how far they ended up compared to where they started here and ended up here. This distance is only 10 kilometers, right? Because they went 10 this way, came back 10 and went an additional 10 the other direction. So they ended up, well, sorry, not kilometers per hour, just kilometers. So they ended up 10 kilometers from where they started. And what direction did they end up? They ended up west of where they started. So the displacement is 10 kilometers west. So we can see that when we have changing directions, then we're going to start getting different displacement versus distance. And this last example is going to involve two dimensions. So it says we go 10 kilometers east and then 20 kilometers north. So if I'm starting here, I'm going to go 10 east and then 20, about double that, north. Okay, distance still pretty easy to find. They went 10 and then they went 20. Their distance was 30. This is in kilometers. Their displacement is a little bit trickier in this case because we're going to say, well, where are they at the end compared to where they started? They start here and they finish here. We want a straight line between those 2 points where they ended up. So I'm going to draw a straight line like this, and that represents their displacement. Although, how do I figure out that number? Well, fortunately, north and east are 90 degrees to each other. So we have a 90-degree triangle here. We know these two sides. Using Pythagorean theorem, we can figure out the last side, which hopefully you remember from math is a squared plus b squared is equal to c squared. So I go 10 squared plus 20 squared, square root, and I'm getting a number there of about 22.36. For this example, we'll just round to 22 kilometers. Now we also have to put the direction. Well, they went east, but they also went north. We're not going to worry about angles yet at this level, but we're just going to put that they went northeast. All right. So that's the difference between distance and displacement. Okay, so I hope those concepts made sense for you. Make sure you try the practice questions, and I'll see you in the next video.